Okay, hi guys, welcome back to the think class of operating system concepts. And today we are going to discuss something about critical sections problem, and the problem are solved using the semaphore variables and primitives. Okay, so before starting the session, let's go to the traditional thought-provoking concepts. Okay, so the thought for today is like invention is better than cure. Just think about it. Invention is always better than cure. Okay, with this thought, now let's start the session. And okay, let's begin the first question then. The first question says that what is a critical section problem then? The topic says critical section problem. What is this critical section problem? The critical section problem is occurred usually when n number of processes are competing to use some shared resources or data. That means there is only one shared resources and there are n processes we are competing with each other process to use this kind of shared resources. And each process has a code segment. So each process has some kind of local memory or some kind of code segment called critical section, in which the shared resources or data is accessed. Okay, so from this code segment you can access the shared resources or data. Okay, now the next question, like how do we ensure that one process is executing in its critical section while no other process is allowed to execute in its critical section? What is the ensuring concept? How do we ensure it? We ensure it by establishing an access protocol, some kind of protocol to ensure the critical section in the mutual exclusion. Okay, so what is this access protocol to the critical section means? Usually these access protocols are of two types and one is called prologue and one is called epilogue. A prologue is something that the process execute a reservation code before entering its critical section. So whenever a process enters a critical section, it executes a code that is like prologue, and it is a code that is called a reservation code. It reserves the space, then it goes to the critical section. Before going to the critical section, it has to reserve the space. Okay, and the code, the particular code that is used to reserve the space is called reservation code, and it is also termed as prologue. And this code will block other process while the particular process is in the critical section. That means this particular reservation code will act as a tool to block so many other processes who are competing to access this critical section. Now, what is the second access protocol? And this second access protocol is called epilogue, and the process leaving its critical section executes a code to release its critical section. That means like whenever a process exits or leaves the critical section after completing its job, then it also release this reservation code. It also executes a code to release this reservation, and this is called epilogue. And this is just a way to say that the critical section is not busy. You can check out here. While true, this is looping forever, and it is like first it does the prologue, that it puts the reservation code, then it goes to the critical section, and later on it does epilogue, which releases the reservation. Similarly also here for critical section 2, same thing happens. So what are the specification of a mutual exclusion then? Mutual exclusion is when one process executes the share variables and all the other processes desiring to do at the same time, okay, must be kept waiting. That means, like, while one process is using or utilizing the critical section, all the other processes which are waiting must wait for this particular process to finish its job. And this particular phenomena or process or mechanism is called mutual exclusion. That means, like, also, until and unless the process finishes its job, all the other processes who are waiting should not be allowed to proceed. Okay, they must be blocked. So this is the way how, like, all the process will have the equal opportunity to grab the critical section and finish their job, right? So if the processes are performing operations that do not conflict with one another, they should be allowed to proceed concurrently. That means also you have to be careful about, like, the process while performing the, like, utilizing the critical section should not affect some other processes. So it must be something independent, okay? And also you can see that the solution is very symmetric. The access do not depend on the relative priority of the process. So the it's not like that the process 1 has priority 1 or process 2 has priority 2, so process 1 must always be stay there. It doesn't depend on the priority, okay? It is something that is without any kind of priority. The solution is very symmetric. That means each process has the equal opportunity to get the critical section, right? Now the solution do not depend on the relative speed of the process, okay? Also the speed of the process do not matters. And the solution allows a process to access its critical section even if another process is blocked outside its critical section. That means, okay, the same thing, like, if there is also another process which is blocked, still the process is allowed to be accessed in the critical section. And lastly, the solution is very deadlock free and starvation free. That means deadlock free means some kind of, like, both the processes are colliding with each other, okay? And starvation free means only one process has a priority over another process. So this kind of situation are avoided here in mutual exclusion. And should, okay, now let's go to the example. In the example 1, you can see the mutual exclusion solution 1, okay? A type of solution that can be implemented is, in this solution, what we are going to see is there are two processes, process I and process J, and the respective code how to access the critical section is also provided here. And in this solution, only one process executes at a time while other process is waiting. Okay, what happens is, like, while forever looping, while this turn equals to J in process I, if the turn equals to J, then nothing happens. Okay, it loops forever. Otherwise, the process I goes to the critical section, then the turn goes to the J, okay, and process I leaves the critical section. This is the thing. Whereas even process J here, the situation is loops forever for process J. If the turn is for process I, then nothing happens. Whereas process J goes to the critical section, this particular process goes to critical section, and turn is set to I. That means this process I will go to the critical section here. When turn is set to I, then this process will have no critical section here. So something like this occurs. And also the point to be noted is, always be careful that we are working with the two processes I and J. I and J processes. Okay, that means when turn is set to J, the critical section should be implemented in this J. Okay, process J. Whereas the turn is set to I, it goes to here. So only one process will be able to use the critical section here. Okay. Now for the second solution for mutual exclusion, we have also particularly there is a code for independent process like process I and J, and what happens is like the flag is set here. While the flag for Z is set, then nothing happens. Okay, in process I. Whereas for flag is I is true, this is the entry section, and if the flag of I is set true, then process I goes to the critical section, and flag after process I finishes its job, flag I is set to false, and the exit this is the exit section, and process I exits, and there is no critical section. Whereas if the flag is set to I, nothing happens. Okay, whenever this is in critical section, the flag is set to I, nothing happens here in the process J. Okay, process J is still waiting. Whereas when flag of J is set to true, that means flag of J is set to true, nothing happens here in process I. Okay, and process J goes to the critical section, and similarly process J is set to false, and when the process J to false, then flag of I is set to true, and PI goes to the critical section. And similarly it works here as the same solution as before, but this here we are setting the flag. There is a flag to be set here. Both the process PI and PJ are in critical section. As the condition satisfied, flag I equals to flag J equals to true. Right here it is said that like flag I is true and flag J is also true, and that means it goes to the critical section. Now the third solution is the solution 3, and this solution is particularly resulting into a deadlock. And now we'll check out how this is resulting into deadlock. For process I, while forever true, like it's true, then flag I is set to true. Okay, while flag I is set to true, then flag J is the this is whole is the intersection in which like flag J is while flag J is set to true, nothing happens here, right? But and the process goes to the critical section, process I goes to the critical section, while flag J is set to true, nothing happens. Whereas flag I is set to false, this is the exit section, so that process I just leaves the critical section. Whereas similarly flag J is set to true, is the entry section, while flag I is set to true, then nothing happens. And this means like something like flag J, here also flag J is I is always set to true. That means it always go to the critical section. Even immediately here in process I, flag J is also set to true. So always this go to the critical section, right? This means like both the process are always true, they are set true, and they are going to the critical section here, right? So this is the cause of the deadlock here. Okay, you have to be careful about this particular section, that is like flag I is always immediately in the loop, flag I is set to true, and also for this was for process I, whereas for process J immediately the flag Z is set to true, and this is going to the critical section, so both will clash and the deadlock occurs here. Now each process PI enters its critical section only if flag J equals to false. Okay, similarly flag I equals to flag J equals to true, so deadlock occurs. Now the last solution is the solution number 4, and let's check out the solution. How to avoid this kind of deadlock is like we are also setting another parameter, not only a flag. We are not only setting the flag, we are setting also a turn. Is it a turn for J or is it a turn for I? Okay, so while this is a turn of J, nothing happens. Okay, the only difference is we set a second parameter, that is we set a turn. If it is a turn of J, nothing happens, and in process J, if it is a turn of I, nothing happens. So this is the way how to avoid the deadlock in this kind of particular situation. Okay, and similarly here is the explanation of how it is done. Like each process I enters its critical section only if either this, okay, the flag I is false or turn equals to I. That means similarly, as I have already told you before, while this is true, nothing happens. Otherwise process I like goes to the critical section. Okay, similarly you have to be careful of all this thing. And now, okay, so what are the drawbacks of this solution number 4 then, of setting a new parameter there? What are the drawbacks? This solution is valid for two kind of processes, but also it can be generalized, but mostly it is valid for two kind of processes, and these are the drawbacks. So it cannot be totally generalized. It cannot be valid for n kind of processes. So if there are some n processes, okay, for example, you can only set it for, you can set the turn for I and J, so just two kind of processes. But if there are n processes, you cannot keep on setting true for I or J, or so there are some combination matters, right? This is only for two processes, that is I or J. Okay, so it is, but cannot be generalized. This cannot be generalized for n kind of processes. Whereas you can also say that like complex prologue entry code and ineffective solution, that is busy form of waiting or spin lock is here. That means unless the busy form of waiting occurs, because unless the PI leaves the critical section, process J will not be allowed to go to the critical section. So if the process I keeps on using the critical section, there is the situation like a busy form of waiting will occur, and this will create a spin lock. Okay, and the complexity is due to the possibility that the process changes or tests a variable, and this operation is invisible to the other processes. That means a process can react to a value of a variable. That means while has been changed. Okay, this was all to explain like the complexity that was occurred due to busy form of waiting is all due to the operation is invisible to other processes. So whatever processes occurring in this process I will be invisible, totally invisible to process J. So this is why some kind of busy form of waiting occurs if process I keeps on using the critical J and start finishing its task until the turn I is set to true, right? Flag I is forever set to true. So busy form of waiting can occur here. Okay, so what are the other kind of solution to mutual exclusion? So some other kind of situation to solve the mutual exclusion in a case of a single processor are, we can use disable interrupt or enable interrupt. Disable interrupt is used as a prologue, that is a reservation code to the critical section, whereas enable interrupt is used as a code to release the critical section. Okay, now for the other kind of solution to mutual exclusion in case of multiprocessor system, having the common memory are like the test and set. And test and set is a special instruction on a log variable, and this log variable is something like some kind of variable having a values, and if a log variable is 0, then the critical section is free, whereas if a log variable is 1, the critical section is busy. So this kind of test and set instructions are available. The instruction test and set test the content of the variable and set it to 1 in a single atomic cycle. And a single atomic cycle means atomic operations. You have to understand, like, atomic operations are the operations that cannot be divided into any smaller parts. So this is a single operation. It acts as like single unit operation which is not divided into so many operations. This test and set is a single operation, and you can check out the pseudocode of test and set. Whatever it does is it tests the content of a variable and set it to 1 in a single atomic cycle. Look, the test condition is passed as a parameter here, argument here, okay, this test variable as a target. Then this test variable is automatically set to 1 in a single atomic cycle. And this is the pseudocode for test and set. This will be used here immediately. Now, how is the mutual exclusion with test and set done then? The mutual exclusion for test and set is done in this way. While true forever, what is done is, while test and set is done here, that means the initial test condition, the variable is for process I is 0, that means it is set to free. That means the critical section is free in this test condition, right? So while the test condition is set, that means it is locked now. While it is locked, nothing happens. That means while the lock variable is 1, here this test and set function will lock the variable, okay, passing the past value variable is the condition is 0. So while we pass the condition here, immediately it will change to 1, and while in this condition it locks. That means the test and set value like condition will set the value to 1, and nothing happens in this case while it is locked. Whereas if it is not locked, then it goes to the critical section, and then lastly it unlocks. And there is no critical section has occurred. And in this kind of situation, the starvation might occur because it is the test and set just sets the value to 1 unless the process I just uses the critical section. It is not unlocked, okay, and it is keep on locking the variable and keep on consuming the critical section. First it locks, then it uses the critical section, and it keeps on using the critical section. So lastly, after finishing the critical section, it is unlocked. So in this kind of situation, the starvation might occur because other processes we are waiting. Okay, so the busy form of waiting might occur, and the starvation also might occur, right? Because it is always busy, the process I will always be busy here, and process J will still be waiting for process I to finish the job. Okay, now how do we do the mutual exclusion with test and set without starvation then? This was due to this caused the starvation. So how to do the mutual acceleration without such kind of starvation is like we have to, okay, it is explained here in this particular code. It is said that while true, waiting is set to true and the key is set to also true. That means while waiting is true and the key is also true, the key is set to, and then we unlock, because lock variable, then we unlock while waiting is also 1 and key is also 1. We unlock the key and waiting is set to false and critical section, the process I goes to the critical section. That means after unlocking, if waiting is true and key is also true, then the key is unlocked, okay, and waiting is set to false, there is no more waiting, so critical section goes, no more waiting and critical section is the process goes to the critical section. Now what happens is like another variable j is incremented by 1, okay, which is just like compared to the modulus of n, and while j is different from I and not waiting, that means j is incremented. Previously I was 0, so 0 plus 1 is 1, module 1 and is 1, j is 1, j becomes 1, so j is different from I, that is 0, and not waiting j means 1, so the next value next of I, that is j, I plus 1, that is 0 plus 1 is j. If the next value of the process, next process is not of next index of the process is not waiting, okay, then j is incremented. Then if j is equals to I, this never occurs, okay, so j will never be equal to I because j is always incremented if there is no waiting. But if there is waiting, then j will be equal to I and the lock is occurred, okay. So if there are, for the same process, if there are more processes waiting, then the process is locked and it waits. But if there is no waiting, then the waiting is set to false, okay, and there is no critical section is also freed here. And this is the situation how we avoid the starvation, because we start checking if there is any waiting, the processes are waiting to access the variable or not, okay. So this is the situation. Okay, now what is the architecture of a multiprocessor system then? As I told you, a multiprocessor system has a common memory. So this common memory is distributed among all the processes having their own independent local memory. So each process have their own local memory, whereas there is a main common memory. Alright. Now, what are the drawbacks? Lastly, what are the drawbacks of spin lock then? Spin lock is occurred while the process I keep on utilizing the critical section, and it doesn't, it just performs prologue, whereas it doesn't release the critical section. It do not do the prologue. So this kind of situation is called the spin lock, and busy form of waiting occurs. Scheduling cannot be controlled by the programmer, and the bus occupation is also occurring. Okay, so thank you for listening. We will continue more in the another noon session. So till then, thank you.